Lesson 312. This is going to be your favorite lesson of the year. I know this is going to be, you've had a lot of favorites.
No.
This one is absolutely going to be your favorite of the year. And I'm speaking very facetiously. This is one though. What is nice is we're going to be able to solve with this. What's not nice is it's going to require you to really think a little bit. So what are we dealing with today? We're dealing with this idea of trigonometric identities. You may remember in lesson 311, gave you a list of some. We're going to introduce a whole bunch of trigonometric identities and walk through what we can do with it. So today's lesson, we can rewrite trigonometric expressions in equivalent forms using trigonometric identities. This is similar to this idea. Do you remember in unit 2 when we had stuff like log 3
And then you
plus
an exponential function.
log 5? Okay, that would be doing the inverse. But there were properties we could do. Do you remember what we could do if you had log 3 plus log 5?
Multiply.
We could multiply what? The logs, would it become log squared?
No.
Just log, and then it'd be 3 times 5.
Yeah.
It'd be log of
15.
15. And we called that the product property. You remember that? Today's lesson is similar. We're dealing with, but they don't call them properties. They call them identities. Because by rule, what's going to happen is identity means you can substitute one thing mathematically for another that's true. For example, here's an identity. Sine. I could substitute sine theta with y divided by r. These are identities because there's two things that are mathematically equal. Today, we're going to go through some trig identities. Okay? So those are two examples there.
R representing radians.
We're going to use radians. It's true. All these are true in degrees as well. All right. So here are what we call the fundamental trigonometric identities. So first, last class, we did cofunctions. I showed you a Desmos graph I created. Cofunctions, it shows you where they get their names. Notice all this in the name, it has co in front of function. So if you put a co in front of sine, what do you get? Cosine. You may remember that if you took any angle, a sine connects to the tangent, point of tangency, to the secant line, which is the x-axis. What did cosine do?
It would connect from the point of tangency to the y-axis.
That's right. The difference is from x-axis to y-axis. Now, how many degrees are between the x-axis and y-axis?
90.
90. Now talking radians. How many radians are between?
5.5.
Okay, so here's what this is saying. Let's just say I had cosine of pi over 3. Use your hand trick. And then here in a second, I'll put pi over 3 here as well. So you would take it, bend it, and you would get, for cosine, you bend your index finger, then your hand. What do you get for cosine there? Nope, that's the sine.
Oh, cosine, you would get square root of 1 over 2.
Square root of 1 over 2, which is 1/2. Okay, now let's come over here. If I were going to simplify this, I'd have to get a common denominator. So I'm going to multiply both by 1, a weird looking 1. This is 3 over 3. This one would get multiplied by 2 over 2. That's a denominator of 6. What is 3 pi over 6 minus 2 pi over 6? 1 pi over 6. Okay, go back to your palm of your hand. What's your pi over 6 finger?
This one.
Your pinky. You bend your pinky, flip your hand. What do you get for sine there? 1 over 2. Notice we get the same answer. So these are what we call, I said pinky. Yeah, it's not pinky, it's your ring finger. Those values are the same. All that to say, these cofunctions are always equal to one another. We have odd and even identities. What this is detailing is whether the negative matters or not. This is all based off whether the function has a y or not. Let me just show you a quick graph. Using this circle here, the unit circle. If the function has a y, a negative angle will matter. If the function does not have a y, the negative angle will not matter. So let me show you. Here's a positive angle. Here is a negative angle. Sine, does it have a y? Yes. So if you were doing sine of theta versus sine of negative theta, you're going to get different values because one's going up, one's going down. And so the answers would be opposite of each other. That's what this negative on the outside is showing you. But over here, cosine, it would not matter because what does cosine measure? X. And notice the intersection between this purple and the orange and the unit circle are the same x location. So if the function only has an x as opposed to a y, the negatives don't matter. That's what these are called. Even functions, put even here. These would be called odd. Odd will be symmetrical with the origin. even symmetrical with the y-axis. Those are even and odd identities. We're going to have Pythagorean. We had quotients. And we had reciprocals. All those we had last class. Reciprocal means to flip. And so another way you can think of the reciprocals, if you're dividing by a cosecant, you can change that to multiplying by a sine. If you are multiplying by a cosecant, you can change that to dividing by a sine. You can think of it that way as well, if you want to put the one multiplying up front. Anyways, those are our identities that we're going to start with. And so I'm going to work our way through here, showing you what can we do with these. I could talk about these all day long. I told you this lesson is going to be really fun. I was being facetious. So let me get to it. It says here, if you know the trigonometric ratios and the Pythagorean theorem, it's not too difficult to derive our identities. Let me prove it to you. What's the Pythagorean theorem? A squared plus B squared equals C squared. Okay. Now for pre-cal sake,
X squared plus Y squared is R squared.
Yeah.
X squared plus Y squared equals R squared. Okay, there were three Pythagorean identities. Let me tell you how they derived those. What if we took all three, this whole function and decided, you know what I want to do? I want to divide everything by R squared. You know, in math, you can do this. You just have to make sure if it's division, you divide everything by R squared. Well, what would I get if I divided everything by R squared? What is X squared divided by R squared? That would be a cosine squared. Because X over R is cosine, so X squared over R squared is
Cosine squared.
cosine squared. The squareds don't cancel. So this would be, that right there would become cosine squared. Let me write that. Cosine squared plus, what's Y over R?
Sine squared.
Sine squared. What's R squared over R squared?
Just R. No.
No. Anything divided by itself. What's anything divided by itself? 1. That's how you get your first Pythagorean identity. All right. So anyways, that's how we develop Pythagorean theorem. I'm going to do this again one more time, and then we'll move on to the next one. Again, if you want to develop any of these Pythagorean identities, you start with the Pythagorean theorem and you modify it in some way. So that's how we would get our first Pythagorean theorem. Now let me show you how we get our second Pythagorean theorem. Let me delete this out of here. Delete this out of here. This time, how you could get another Pythagorean theorem, and these are important to know, a Pythagorean identity, is you start with your Pythagorean theorem, and last time I divided by R squared. What's a different letter we could divide by?
Y squared.
How about Y squared? What if we divided everything by Y squared? What would we end up with? We're going to come up with another Pythagorean identity if we did that. What is X squared divided by Y squared?
Cotangent squared.
That's cotangent squared. What's Y squared divided by Y squared? Anything divided by itself is 1. And then finally, what's R squared divided by Y squared? The reciprocal of sine. What's the reciprocal of sine? Cosecant squared. So if you have to formulate or come up without a formula chart with the Pythagorean identities, you start with the Pythagorean theorem and you just divide by letter. We could do this again. What's the only letter we have not divided by? X. You can divide by X squared and get the third Pythagorean identity. Okay, so now let's come over here and I'm going to talk about even and odd functions. I kind of drew this a second ago. Even and odd talk about if a negative would matter. So here, I want you to look at a sine value. And then I want you to look at the sine with a negative angle. So let's talk about sine. What does sine measure? The y divided by the radius, which in this case, r is 1, because it goes from 0, 0 to 1, 0. So it'd be y divided by 1. Okay, what happens if you have a positive angle? Tell me about the y. Is it positive or negative? Positive. This would be a positive sign. However, if you had a negative angle, what type of y value would you have? A negative. And so this would be a negative sign. This is a odd function. It's odd, meaning that if you have a negative angle, the sign will be the opposite of the sign of with a positive angle. And you can go work your way through all of these. I'll do 2 more. Let's talk about cosine. Let's say we take cosine of this theta right here. What is cosine's ratio? Guys,
look,
here.
X over R.
It's x over r, which would be x over 1. It would be a positive x because we are on the right side. So cosine with a positive theta that's representing this circle would have a positive x value. It would be the length to there. Okay, now let's talk about the cosine with a negative angle. So if I took the same angle, but just this time made it negative, nothing different about it, the measurement, but just had it a negative. Tell me about this x value here. Is this x value positive or negative? Positive. Okay, so look at this. Does a negative angle have any effect on a cosine?
No.
No, they're the same signs, but did it have an effect on the sine?
Yes.
What's the difference?
One
Sine includes which variable?
Y.
A y. If it has a y, it'll make a difference. Let's do one more. Tangent. If I took the tangent at this angle, sine is y, cosine is x. What is tangent?
Y over X.
This is a positive y divided by a positive x. What happens when you take a positive y and divide it by a positive x? Do you get a positive or negative number?
Positive.
A positive. So for this theta that's shown right here, you would have a positive tangent. Well, now let's talk about what if we took the negative of that angle. So now I'm looking at this one. I would take my negative y and divide it by x. What's a negative y divided by a positive x? A
You get a
negative or a
negative.
positive?
You get a negative.
A negative. Okay, so this would be even or odd?
So it'll be odd.
That would be odd. So odd means the sign changes. If the angle changes from positive to negative, the sign of the function itself will also change. These two are odd. Cosine is even. You can figure out which ones are odd and even just by doing a quick drawing. Just ask yourself, would it change my answers? Yes, it has a y, then it's odd. It means it'll alternate across the origin. It'll be symmetrical. Let's do that right here. Symmetrical with origin. That's important to know in a coupling lesson. Symmetrical with origin. Even is symmetrical with respect to the y-axis. With respect to the y-axis. I'm just going to say with y-axis, but it's technically symmetric with the y-axis. Okay, and one more I'm going to do here just to prove how you can find these are the cofunctions. These shouldn't be that hard. You shouldn't need that much help because you really just put the word co in front of it. But a cofunction, if I talked about sine of this angle, sine of theta, what does sine measure? This y value divided by r. So it's taking this y over here is the same as this y. It's this y divided by 1. So sine would measure that. But if I look at the angle of pi over 2 minus theta, if I'm looking in this triangle, if from this perspective, if you're looking from here out, this is no longer considered the y-axis. If you were looking at this triangle with this angle, this is similar in standard position to an x-axis. Notice this would become the x. So that would be equal to cosine of pi over 2 minus theta. So we call those a cofunction because the angles are complementary. Sine becomes a cosine, tangent becomes a cotangent, secant becomes a cosecant. Those are easier to formulate though, but that's what this diagram is to show you from here. Okay. After going through that, let's actually use these to solve. So let's look at example 2 here. It says verify each equation using trigonometric identities. What it means by verify is I'm giving you two things that are equal to one another. These two things are equal. We're not solving to find out when it's equal. These are equal all the time. And every theta or every, in this case, alpha, any alpha beta, any alpha value you plug in, this will always be the same. Now, why is it the same? What this lesson's all about is showing you how we can exchange things to simplify. Now, what I'm going to do is always start on what I call the complex side, and I'm going to work towards the simple. So I'm going to start from the complex and go to simple. So I'm going to start over here. Well, sine is already simplified, but secant, we could rewrite secant using a reciprocal identity. Secant is the reciprocal of which function? Okay, so I can rewrite secant. That secant is multiplying. I can rewrite it as a cosine dividing. And so I started with this side Now, what is sine times 1?
Sine.
So that becomes sine over
Y over X.
cosine, which that is the same thing as y over x, which by identity, what is y over x?
Tangent.
That is tangent.
And that's just how.
And so some people, this is called the proof, what we just showed. Some people do a box at the end and fill it in, just saying, hey, I'm done with my proof. Other people just do a check mark. That's what I'm going to do, a check mark. Now I'm going to name the steps. What identity was it when I did a reciprocal? Simply put, it was called a reciprocal identity. That was a reciprocal identity. I did. Now, saying that sine over cosine is the same thing as tangent, that's what we call a quotient identity. This right here was a quotient identity. If you look back, that's where you'll find that on that chart, because tangent as a quotient, what does quotient mean again?
The answer.
Division. The answer to division. Tangent is the answer to the division of sine divided by cosine. So most of these names come from what you're doing to the sine or cosine to come up with the function. So what am I doing with the sine and cosine? I'm dividing them. That's why we call it the quotient identity. All right, let's try this one. Over here, don't worry about what the angles are. They could use A's, they could use B's, they could use thetas, they could use X's. It doesn't matter. We do the same thing. I'm going to start on the complex side. What's the complex side here? Okay, Armando. Hey, with me, not on that. This is cosine beta times tangent beta. Got to know your Greek letters here. Equals sine beta. Okay, I'm going to start on the complex side, and we work from complex to simple. So on the complex side, what could we do? What could we break down in terms of a sine or cosine? Tangent. What is tangent in terms of sines and cosines? Which is sine over
Sine.
cosine. All right, what was the name of this? Like, what am I doing in terms of sines and cosines? I'm dividing.
The quotient.
So this would be called the quotient identity. That was by quotient identity. That is equal statements. Okay, now what could I do here?
You just cancel out those cosines.
We could simplify and say that is equal to, if I cancel those cosines, this is just equal to sine B, and we're done.
That's it.
That would be it for these first two. And by the way, when you get to your delta math, most of the problems are going to look similar to this. They don't get too complex. I'm going to show you stuff that's a lot more complex, but delta math keeps it pretty basic. That would be your answer here. Okay. Let's go on to example 3 and show us. Let's look at all right, let's look at some different properties. So here, circle this up. We're going to use the same identities I showed you, but this time I'm going to incorporate some algebraic principles. So what does this mean? We're going to be looking for things like factoring, combining like terms, stuff like that.
It's like we're doing everything.
So yeah, here's what you can say. We're taking our algebra 1 and we're adding algebra 2 plus trig. And like I said, I did this math equation the other day. This is going to equal awesome. No,
Nowhere close to awesome.
it's awesome. Okay, that's what we're doing here. So here we go. Picking back up. Which side's the complex side?
The left side.
Everything.
The left side. Okay. All right, so here we go. Let's pick up. So what's an algebraic principle I could do here? Well, I have a fraction that has a difference up in the numerator. What I could do first off is I'm going to separate these into two different fractions. These are terms right now, they're not opposites. For this to cancel, this cosecant is dividing. I would need it to be multiplication in the numerator, so I can't cancel. So I'm gonna erase the cancel here because we can't do that. That's not opposites. So we erase that out of there and let's pick back up. What I was doing before we said let's cancel those is I was saying we can look at this as not a common denominator. I mean, it is a common denominator. I'm separating it out into multiple fractions. So I have sine divided by cosecant over, or excuse me, minus cosecant divided by cosecant. What I did here is I broke apart the fractions, meaning broke apart the fractions. They have a common denominator here. I'm just going to say common denominator as the step here. They're a common denominator. I'm going to just write it this way. Denominator. There we go. Denominator. So I do that step. Okay, so now what can I do?
You can cancel out the bottom two.
You can turn
What is cosecant divided by cosecant?
What?
That's just going to become a 1. Now over here, we can do something else. I'm dividing by cosecant. I could multiply, dividing by cosecant is the same thing as multiplying by, it's reciprocal, not opposite, reciprocal. Which one's the reciprocal of cosecant? It's sine. So cosecant right now, if cosecant's dividing, that's the same thing as multiplying by a sine. Now it's called a reciprocal identity.
Right, so the formula equation for cosecant is R over what?
Cosecants, let me write it this way. If cosecant is dividing, that's the same thing as multiplying by a sine.
Oh, because sine is y over.
Because there's reciprocal. So you could say it's like sine times 1 or whatever. But dividing by cosecant is the same thing as multiplying by a sine. Okay, so now I'm back over here. What is sine times sine?
Sine squared.
That is a sine squared minus 1. Now, what I'm going to say about that is equal to cosine squared, and we're done. And you don't know why, but I'm telling you that we're done. That is an identity there. Now, you might not know what identity it is, but I'm going to tell you the hint here. Anytime you have two squareds or a squared and a plus or minus 1, it doesn't matter if it's a squared plus or minus another squared, or if it's a squared plus or minus a 1, it's going to be the Pythagorean identity. Now, why is that the case? What we wrote a moment ago is that sine, we wrote it in this order. We said that cosine squared, hey guys, here. We had it with a theta. We said, no, I'll use x because whatever. We had cosine squared plus sine squared equaled 1. That's what we had earlier. Well, if I did some algebra to rearrange this, I could subtract a cosine from each side. Oh, and I see I got a typo on this. I could subtract cosine from each side. And I could subtract 1 from both sides. I want to put the negative there. I got to fix that. And then what do we get here? These are opposites. They cancel out. I have sine squared minus 1 equals, 1's cancel out, negative cosine squared. And so this needs to be a negative. It's just a typo. So that's how these identities work. What we're doing again today is we're going to be doing some algebra 1, algebra 2 along the way, and some trig identities to simplify an equation. So that was part A. Let's try part B. Now, this round of example 3, what's going to make it different is we're going to use algebraic principles. So that one was the common denominator. That was the algebraic principle. Okay, what about this time? All right, let's see what happens this time. Example 3. I'm going to work on the side with the fraction. I think that is more, I think that's more complex. I'm going to call this the complex side here. You always work from complex to simple. Okay, so let me walk you through here. A tangent. Right now, we're dividing by a tangent. I want to get rid of the fraction to try and make this simple. I'm going to get away from the fraction. So tangent dividing is the same thing as multiplying by which front function?
Cotangent.
A cotangent. That is called a reciprocal identity. Now, what I'm going to do here is I'm trying to simplify this to become this function right there. Do you follow? Trying to make this, or trying to make this right here become that. I know where I'm supposed to get. So right now, what I want to get to is secant times cosecant. Right now, I have secant squared times cotangent. So here's what I'm going to do. I'm going to change these into, I'm going to first break apart this secant. Now, why do you think I'm going to break apart this secant?
Because secant is cosine, it's just one with both.
Oh, okay, well, we'll get to that in a second. That's going to be the next step. Because it is squared here, so I'm writing it as secant times secant. It's the same thing as secant squared. Why I'm writing this is where I know the final goal is. How many secants do I have over here? One. So I'm going to break them apart because I know one of them's got to cancel somehow. Now, that part is just pure algebra. That a squared is the same thing as anything times itself. But what is cotangent equal to? What can I change that to? X over y, which is cosine over sine. Now that right there is called the quotient identity because the names come from basically what is happening with the sine and cosine, not what's happening with cotangent. The names come from what's happening with the sine and cosine. We are dividing them, so we call that a quotient identity. Hey, Chris. Now from here, how could I simplify?
You make the secant into 1 over cosine.
Okay, and I'm only going to change one because I know I need to have one secant in my answer. So I'm just going to change this secant. What could we say that this middle secant? Secant's the same thing as what in terms of sines and cosines?
1 over cosine.
It is 1 over cosine. Now, when I change a secant to a cosine that's dividing, what type of identity is that? It's a reciprocal. Very good. It's a reciprocal. Now I have one more step here.
Cancel out those two cosines and then sine becomes just sine.
We are going to cancel those. So I'm going to have secant. I'm going to do one more identity. I am canceling those. I need this to become, I'll write it this way. Secant times 1 over.
Sine, which is cosine.
Very good. I'll write it like that. And we're going to say that equals a secant times a cosecant. By what identity? What makes a 1 divided by sine?
Reciprocal.
A reciprocal. This is a reciprocal identity. And whenever you're done, you can either do that box or in this case, I'll just do a check mark saying we verified that these are equal to each other. Now, what I could also do if we were allowed to use the calculator is I could have graphed this on the left and then graphed it on the right, and you would see that they are the exact same graphs, which means they're always identical to one another. That's why we call this an identity. They're always identical to one another.
Can you graph both of those to make sure?
Yeah, I could. If we wanted to graph them to make sure that these are accurate, menu, graph. The first one is, whoops. The first one is secant. By the way, on the Inspire, you need to use the variable x, and squareds go on the, or any power goes on the outside of your parentheses over tangent. That's my first equation. My second equation is secant x times cosecant. X. What can you tell me about those two graphs? There's one. Here's one. There's the other. These two graphs are exactly the same. So what does it mean if they're the same graph? They're equal. So they are equal to one another. All right, let's look at example 3. So again, ignore the variables. The variables do not matter on this. Doesn't matter if they use an alpha, a beta, an x, a theta, doesn't matter. So we're going to go through solve. Obviously, the left side's more complex. So what do you notice what do you think we could do to try to make this into tangent? We could split the square. I would actually,
What about
Well,
converting those
sure.
secants and cosecants?
all right, let's do that. We'll do both at once. So sine squared is the same thing as sine times sine, okay? Secant is the same thing. Multiplying by a secant is the same thing as dividing by which function? Cosine, good. And then multiplying by a cosecant is the same thing as
Divided by sine.
dividing by a sine. What did I do there? I did two reciprocal identities. We did two of them. Reciprocal here and there. Now, what do you think we can do from there?
You can cancel that. With sine.
One sine with one sine.
You multiply sine.
Sine times 1, which is sine divided by.
You do reciprocal identity.
Close. You got the right algebra, the wrong name. So the name's not based off of the tangent. It's based off of this. What's happening with the sine and cosine? Are we doing a reciprocal here?
Quotient.
That's a quotient. Very good. That's a quotient identity, and that would be the name. Quotient identity. And so these would be equal. Again, if we graph these, you would get that this that we started with is equal to tangent. All right, how about? Not done. Okay, give you a second longer. So a lot of these are just changing identities and simplifying. Sometimes you're gonna have to do more algebraic tricks. So on this one, let's see, what can we do on this one? What do you think we could do to make this more simple?
Simplify the tangent.
So I'm gonna go through here. Sine, I rarely change sines and cosines. Those seem are the most basic. Most everything's based off of sine or cosine. The identities are. So I leave that alone. I could change the tangent. What do we know tangent is in terms of sines and cosines? Okay, so I'm gonna change that to sine over cosine plus cosine. Now, changing a tangent into a sine divided by a cosine. Again, the names come from what's happening with the sines and cosines. If it's a sine divided by a cosine, what should we name that? That's a quotient identity because the sine is being divided, quotient, by cosine. Now I'm going to do a algebra trick here that I did earlier, but I did it the opposite direction. This time, I'm going to combine these together into one fraction. If you're going to combine something into one fraction, you have to have a common denominator. So what I'm gonna write here, what is sine times sine?
Sine x squared.
Okay, and the way we write that is we put the square, the angle itself, the x, is not what's squared. That angle, let's just pretend it was 30 degrees, would stay the same, or pi over 6, it would stay the same. But the sine itself, that's what's squared. Over cosine plus, to get a common denominator here, I need to multiply this cosine by a funny looking 1. I'm going to multiply it by cosine over cosine.
You mean times, not plus?
Multiply.
No, I'm talking about the little symbol you put in there.
They were adding.
Okay.
This cosine was here, so that should be there. Now this is just getting a common denominator. That's all I'm doing here. So now that I have a common denominator, I can write this as one fraction.
Cos X.
This is sine squared,
Would it just be 2 cos X instead of?
not 2. When you're multiplying, you don't change the coefficients multiply, which is 1 times 1, still 1. But what's a cosine times a cosine? Cosine squared. Okay, I need to get a common denominator here. So on this side, my denominator is cosine. Over here, my denominator is like a 1. So to get a common denominator, I need to multiply by cosine over cosine. It's a funny looking 1. Now I have a common denominator. You see how the denominator is the same? So I make one fraction. This was sine squared. It needs to add with cosine times cosine. What's cosine times cosine? It's not cosine with an x squared. It's cosine squared x. And now I can continue on. We good there? I had a common denominator. This right there, I just simplified. I didn't do anything other than I simplified. If you want to name this one, I just simplify. That's all I did there. So let me take away that little dot, simplify. Okay, so now I can do an identity. Sine squared plus cosine squared. Anytime you have a squared plus or minus another squared, or a number 1 plus or minus a squared, you can do the Pythagorean. Go back to your Pythagoreans. What is sine squared plus cosine squared going to equal? Well, if you don't want to go back, think about how to formulate it. Pythagorean theorem is x squared plus y squared equals r squared. Here's how you can do it on the, you're on the ACP, not the ACP, I'm sorry, the AP exam. You're like, oh wait, what's that equal to? Here's what you do. How do you get a sine squared? What creates a sine squared? Oh, sine, sure. What's the ratio? Sorry. What's the ratio?
Y over R.
Okay, so we need to make it a sine squared. It needs that needs to be divided by r squared. Well, if I divide this by r squared, guess what I have to do all the way through?
Divide by R squared.
Okay, so if this is cosine squared and this is sine squared, what is cosine squared plus sine squared?
What? 1.
Not r squared over r squared. It's equal to 1. This numerator is equal to 1.
Oh.
That's the Pythagorean identity. Actually, I'm going to put this Pythagorean on this side. No, I'll leave it right there. That's the Pythagorean identity, but we now have our answer because that's going to equal secant x, and that right there is called the, what's the identity there? Reciprocal identity. And we're done. So I'll put the check mark there. Okay. So you've seen me do a whole bunch. This is the algebra trick that's probably the hardest, the most forgotten thing. It comes from what's called the difference of squares.
The exponent.
The difference of squares. I don't know if you remember this, but in the different in algebra 2, you had a formula for difference of squares that said, I'm trying to think of if they did A's and B's. I think that's how they give it to you. I think they write it as A minus B times A plus B equals, if you distribute this out, what's A times A?
A squared.
Now you would have a positive AB, but then you would have a negative AB. Those would cancel out, and so you'd be left with negative B times positive B. Okay. Anytime you're working through, I told you a second ago, and you have a 1 and a squared, a 1 plus or minus a squared, you can do the Pythagorean. As you look in this problem, I have a 1. Do I have a squared with it?
Nope.
So here's what you're going to do. Anytime you see that 1 and it's not a squared, you're going to multiply by what's called the conjugate. That means you're going to multiply by the factor it's missing in the difference of squared. We're going to call it a conjugate. So right now I have a 1 minus sign. So if I have, that's A minus B. 1 minus sign represents A minus B. I need to multiply by A plus B. I'm going to multiply by 1 plus sign. Now over here, I'm just going to leave it alone for a moment. Sine X over cosine X.
Can you run that back again a little?
Yep. Okay, I've only, all I've done here is I multiplied by a funny looking 1. This is multiplied by the conjugate, is what I'm going to call this. You could just call it conjugate. Multiply by conjugate.
1 minus sin x to cancel out the one on the bottom.
Say that again.
Wouldn't it be 1 minus sin x to cancel out the?
Okay, so it has a 1 minus sin x. I don't want to cancel here. Mathematically, what I want to do is I want to use difference of squares. Imagine A being 1. 1 minus sin x. You see how I'm starting with 1 minus sin x? What I'm going to multiply by is 1 plus sin x. 1 plus sin x. Why? Because that will give me a squared minus b squared, which is going to be the Pythagorean identity. Okay, so just watch what happens here. Let's multiply through this. What's 1 times 1? I'm going to do the denominator here. What's 1 times 1? 1. And then I'm going to have 1 times a positive sign. But don't write it because coming right after it is a negative sign times 1, which is a negative sign. What happens to a positive sign next to a negative sign?
They cancel.
They cancel out. And so they're gone. But what's a negative sign times a positive sign? A negative sign squared. In the numerator, I have cosine times 1, which is cosine x, and then cosine times sine, which I'm going to write as a cosine x sine x, minus sine x over cos x. So here, all I did is I simplified that distribution. I distributed. That's all I did. Distribute. I multiplied that out using the difference of squares as the shortcut there. So now what can I do? Well, anytime you see a 1 and a squared, a 1 plus or minus a squared, what should you always think of? I told you this earlier. It doesn't matter which trig function. If you see a 1 and a plus or minus a square, you should always think of Pythagorean. Let's figure out what this is equal to. I'm going to take the Pythagorean theorem, which is x squared plus y squared equals h squared. I need to have a sine. What's the ratio for sine? Excuse me, I need to have a sine squared. What's the ratio for sine squared? Y over r, and both of them being squared. So I'm going to divide this y by r squared. Now, if I divide one thing by r squared, I have to divide everything. I put an h there. I'm sorry. That's a habit from regular pre-cal. They use h's for triangles, hypotenuse. Okay, so let's simplify this. This would become what? What is x divided by r? X over r is what function? Cosine. So x squared over r squared is
Cosine squared.
cosine squared. That's a cosine squared plus
Sine squared.
a sine squared equals 1. Well, that's almost the form I have. What I have is 1 minus sine squared. So if I subtract sine squared from both sides, that gets me, I have 1 minus sine squared. What is 1 minus sine squared equal to?
Cosine squared.
Cosine squared. That right there is cosine squared. Let me do it in purple so you can see where I got. That's going to be, the denominator is cosine squared. Up in the numerator, I'm just going to leave it like this. And what's the rule with fractions to add and subtract? What's the rule you got to have? Common denominator. You see how it's a cosine right now? If I want to make this cosine squared, I'm going to have to multiply by another cosine. So it's going to become a sine times a cosine. Actually, hey, I'm going to reorder this because it'll matter in a second. I'm gonna do it cosine times sine. Mathematically, it's the same thing, but it'll make a difference over here. So that step right there, we did a Pythagorean identity. I did a Pythagorean identity, and I also got a common denominator.
I'm a little confused how you went from the distributive part to the Pythagorean.
Okay, anytime you see a 1 and a squared, you're always gonna have a Pythagorean identity in trig. It just mathematically, that's just what you're gonna do. So what I did is I took the Pythagorean theorem and first figured out how do I get a sine squared to figure out what its Pythagorean with. Sine is y over r. So to get a sine squared, I had to divide everything by r squared. Once I did that, I got my Pythagorean identity that we were actually using, this one. I have 1 minus sine squared, so I subtracted sine squared from both sides. And so now I can state with confidence that 1 minus sine squared is the same thing as cosine squared. And so I just replaced that with cosine squared. Now over here, I got a common denominator. Why did I do that? Because with the common denominator, I can write it as one fraction. I have a cosine squared for both. So I'm going to write this as cosine squared. What is a cosine plus a cosine times a sine minus a cosine times a sine? Check that out. Look closely. I'm adding a cosine sine and I'm subtracting a cosine sine. Those cancel each other out. These are opposites. When you subtract, those are opposites. They go away. And so what am I left with?
What the hell?
So it's cosine divided by cosine squared, which can become. Hey guys, can y'all quit playing with each other, whatever you're doing over there? Cosine divided by cosine squared. Can I simplify that?
Oh, yeah.
To what?
To one.
To 1 over cosine. I can cancel 1 cosine with 1 cosine. 1 cancels with 1. And so what does that equal to? That is equal to secant. And we're done. What's the name of that step? A reciprocal.
Wait, so wouldn't cos squared x minus cos x times cos x just be 0?
Okay, let me go back up here. No, these two cancel each other out and those become a 0. So it's cosine plus 0, which is just cosine. These two are opposites. I'm adding a cosine times a sine. I'm subtracting a cosine times a sine. So those two are opposites. They could combine because I now have a common denominator. And so those were opposites. They canceled out. And that's how we got that identity. Now I told you, this stuff is no joke. This lesson is no joke. Sure. All right, you've seen me do it. E is what, 5 times? All right, I have one for you to try. And I'm going to give you a hint. When you look at this equation, look on the left side. What do you notice you have on the left side? A 1 plus sign. Is that a Pythagorean right now? No, for Pythagorean, you either need a squared plus or minus a squared, or you need a 1 plus or minus a squared. You need to come up with a squared. You need to multiply by its conjugate. Start with the left side, see if you can come up with the right. Go ahead, DOL number 1. All right, picking up. As we proceed on now, I'm going to show you some angular trigonometric identities. So the identities I gave you earlier had to do with the functions themselves. Specifically, we call them foundational because all the other identities are built from them. With angular, what it means is I'm going to be adjusting the angle now. So I have a sum and difference. By the way, you need to know sine and cosine. I included tangents, so you don't have to have that memorized. You're going to have to know sines and cosines formula by the time the AP exam comes around. I'm going to give you note cards and everything else, but you're going to have those memorized. Double angle, half angle, you don't have to have these memorized. Half angle isn't on the AP exam. Double angle is. However, double angle you can find just by using the sum and difference. If you memorize this one, you can do A plus A instead of A plus B, and you'll end up finding this equation or
we don't get
these.
a reference
No. No, you gotta know it by heart. So we're gonna have to memorize some stuff. So we're gonna work on those identities now. So they're all right there. That's a lot. Okay. So what are we gonna do? We're breaking now and we're going different gear. We're not simplifying equations. Now we're gonna find exact values. Hey, what's sine 5 pi over 12? Let me see. Let's go to your left hand. Looking at your hand. Bend your pi over 12 finger.
I guess by.
We don't have a pi over 12 finger, do we? We have a pi over 2 finger, a pi over 3 finger, a pi over 4 finger, a pi over 6 finger, and then a nothing denominator finger. Do we have a 5 pi over 12 finger? No. So here's how you can do this. We are going to find two numbers, two values that add to be 5, but will reduce with 12. So what am I saying? Two different fractions. You can choose any two, add or subtract, by the way, that will add to be or subtract to be 5, but will reduce with to become with the number 12. What are two numbers that we could choose? For example, here's a bad one. We could not do 1 and 4. 1 and 4. 4 does reduce with 12, but does 1 reduce with 12? Couldn't do that.
What about 2 and 3?
2 and 3 would work. So what I'm going to do is I'm going to find sine of, what's 2 pi over 12 reduced to become? Pi over 6 plus 3 pi over 12 becomes pi over 4. And now I can use my hand trick to solve this. Now you need to know the formula. Here's how the formula looks. On the previous page, or the previous slide, they call this A, they'll call this one B. So the formula is that sine of, let's call this just A and B here. Sine of A plus B will equal sine A times the cosine of B plus cosine A times sine of B. This is A, B, A, B. This is called a sum identity. That right there was a sum identity. If you're looking on the formula chart, it says sum and difference identities. Why is this one a sum? Because what are my two angles doing here? They're adding. It's A plus B. Therefore, it's called a sum identity. The sign was adding. So now we can use our hand trick and we can solve these. Okay, let's do sine of pi over 6. Looking at your pi side of your hand, that means the palm of your hand. Palm, pi for palm. Which finger do you bend for pi over 6? Ring. Bend your ring, flip it over. How many y's do you have there? 1. So it's square root 1 over 2, which is just 1/2 times. Okay, flip your hand back over. Pi side of your hand. Cosine pi over 4. Which finger is pi over 4? Middle, bend your middle finger. Flip your hand over. How many cosines do you have there? So square root 2 over 2. Abdil. So you're with me, please. Plus pi side of your hand, cosine pi over 6. Which finger is pi over 6?
1 over 2.
Ring, bend the ring, flip it over. It's not 1 over 2.
3 over 2.
It's square root 3. We have 3 cosine fingers, so square root 3 over 2 times sine of pi over 4. Which finger is that?
Ring.
No, middle finger. Bend your middle finger. Flip your hand over. How many y's do you have there? Square root 2 over 2. We reduce and we'll have our answer. 1 times the square root of 2. You can multiply square roots. It's just 1 square root of 2 over.
It's not in cosine. Is it because they cancel out?
They don't cancel out. That is the value. A sine pi over 6, sine of the angle equals the ratio. This would be the y radius. The y is half of the radius. That's the ratio here. This becomes the square root of 2 over 4. How did I just get that? What's 1 times square root 2? And then 2 times 2?
4.
Or you do multiply square roots, you do multiply denominators. Over here, what's the square root of 3 times the square root of 2?
6.
Square root of 6. What's 2 times 2?
4.
Okay, when you add and subtract fractions or add and subtract square roots, they don't change. Square root 2 plus square root 6 cannot be simplified.
Damn. So that's our answer.
I'm gonna do it as one denominator, and I'm gonna say it's the square root of 2 plus the square root of 6. There's your answer right there. Go ahead. That's the exact value, by the way. What does it mean to be exact value? No decimals, that's the value. If you type that in the calculator, sine of 5 pi over 12, it'd give you a crazy decimal. You could type this in, and it's a crazy decimal. You'll see those answers are exact. All right, let's look at part B. Let's do this again. What about cosine of 7 pi over 12? What we need to do is what?
Dang, this pack is extra long. Oh my
I
god.
made sure it's extra long.
Do I have a 7 pi over 12 finger? Do I have a pi over 12 finger?
No.
So what do we need to do? Choose two angles that could, two numbers that could simplify with 12. That add or subtract to give me 7. By the way, you don't have to do addition. You could do subtraction. You'll get the same answer. Doesn't matter. What two numbers y'all want to choose that could both reduce with 12?
4 and 3.
I hear 3 and 4. I agree. Both of those reduce. So what does that mean? My formula, this is my A, this is my B. This will simplify first. I'm going to simplify and then we'll type it into the formula. 3 goes into 12 4 times. 4 goes into 12 3 times. These are our values on this problem. These are A and B. Sorry, this is A, this is B. I shouldn't have done it right there because those weren't simplified. Let's look at it this way. So this is a cosine sum formula. So what is the sum formula?
Cosine,
It's-
it would be cos A
That's right. Cosine of A times
times cosine beta minus sine A.
That's right.
minus Sine beta.
cosine A times cosine B minus cosine's formula changes. So it's a plus there. It becomes a minus over here. Minus sine A times sine B. This is called a cosine sum identity. You could just actually say the sum identity. You don't have to put cosine. I did there. I didn't do it on the previous one. Let me erase that since I didn't do it on the previous. That's a sum identity. It's a sum because the cosine over here is actually adding. Even though this part is subtracting. All right, let's use our hand trick and get our solution. Cosine pi over 4. We're looking on the pi side, so I need to look at my palm of my hand. Which finger is the pi over 4 finger? Middle. Bend your middle finger, flip your hand over. How many cosines do you have there? So it's the square root of 2 over 2. Now, if you want to be quicker, we could jump and do the same value as sine. What's the sine at that location? It's also square root of 2. Okay, let's flip back to the palm side of our hand. Now we'll do our pi over 3. Which one's our pi over 3 finger? Index pointer. Bend your pointer. Flip your hand. How many cosines do you have there? 1. How many sines do I have there? 3. So it's the square root of 3 over 2. We're going to simplify this. This time, I'm going to just note it. We're going to have a common denominator. What's 2 times 2? What's 2 times 2? Common denominator. Subtraction here. I can multiply square roots, but you cannot add and subtract them. So these will be separate. What's square root of 2 times 1? And it's subtracting. What's square root of 2 times square root of 3? Because the cosine formula, if you look at on the formula chart, here it is. Cosine, if your angles are adding, mathematically, you have to subtract the 2. So sine's symbol stays the same. Notice the alliteration. Sines will stay the same. If you're adding, you add. If you subtract, you subtract. Sines stay the same. Cosine changes. Cosine, if the formula says if you're originally adding, it now subtract, or vice versa. Subtract becomes addition. Therefore, tangents, if you simplified it, would be the same in the numerator because that's sine. The denominator would be changing, cosine. But you don't have to have that one memorized. You don't have to have tangent memorized. You do have to have sines and cosines memorized. Okay. Where did we leave off? So I'll circle it up. That's it. That is the answer.
Oh, boy, I want,
All right.
why do you have to torture us? That's-
Your DOL. Find two numbers that add or subtract to give you 23. Because do we have a 23 pi over 12 finger?
Nope.
No, you need to pick two numbers that'll either add or subtract to be 23, but we'll simplify with 12. DOL number 2. All right, now let's go to example 5. It says, suppose sine A is 4/5 for a quadrant 2 angle. So sine is what variable, x or y?
What?
Okay, here's what I do first. Draw a line of, let me do it this way. 4/5 of the way. This is 1, 2, 3, 4. I didn't go big enough. Let's go a little higher. Okay, 1, 2, 3, 4, 5. Sine, it means I have 4/5. That's the point that's straight in line right there. Draw a point and an arrow going through it. That right there would be a sine of 4/5, because this point is kind of lined up with 4/5 of the way up to 1 there. Sine B is 1/2 in quadrant 1. 1/2 means I'm halfway up. So halfway up would be what mark? It's not lined up very well. 1/2 should be approximately, 3/5 isn't 1/2. Somewhere in here. Draw another point. Draw a line. Okay. So that's when we have sine B equals 1/2. Now it says, find the exact values of the following. So here's how you can do this. And I think this is a whole lot easier from triangle perspective. The reason I had you draw that is we're going to add in a triangle. Draw a triangle that connects to the x-axis. Always, always, always go to the x-axis. Like this. Okay. Right now, here's what I know. For angle A, I'm going to call this triangle A over here. And this one will be my beta, triangle beta. For triangle A, here's what I know. The y value is 4 if the radius were 5. I know this radius is technically 1, but because of similar triangle rules from geometry, I could say, well, I'm just going to multiply everything by 5 and get rid of my denominator. I'm going to treat the radius as being 5, or the hypotenuse as being 5, and I'm going to call the y value 4. What would the x value be? Do any of you know your Pythagorean triples?
3.
It's a 3. Now, because it's going left, I'm going to call this a -3. Now, if you didn't know that, you would just use this formula. X squared plus y squared equals r squared, or in this case, h squared. And you can get that that's a 3. Because it's left, I'm going to call it -3. Okay, come over here. What do I know about my y value on this problem? It's 1 if this were,
2.
if my radius were 2, this value would be 1. Now I could do Pythagorean theorem, but this is a hand trick value. So go to your rack your hand. Let me write it this way. Beta would equal sine inverse of 1/2. So go to the back of your hand. Back of your hand. If you had 1 sine, bend that finger. What angle do you have?
5/6.
5/6. And it also happens to tell you your x. What's your x?
3.
Square root 3. So square root 3 is my x on this one.
Radius is 2.
And this is pi over 6. That's right. This would be the ratio. Either way, that's the ratio. Now, drawing this as a triangle, you could do Pythagorean theorem to solve those values. But what's going to happen on your AP exam, at least the questions I've seen, it's a very basic mathematical ratio here. It's more a complex consideration. Do you understand what's going on? Now I can find my values. What is cosine of A? That means you look at this triangle. Cosine is always what ratio? X over R. Or in this case, you can call it X over H. My answer is -3/5. What is cosine of B? this triangle,
The X overall, right, so you do X E.
square root 3 divided by 2. Very good. Okay, if I want to find cosine A plus B, the formula would be for cosine, I forget, does it change or does it stay the same, the symbol? Changes.
Is it, hold on,
No,
if I can get.
it changes.
Changes, that's right. It's gonna be cosine A, go ahead, I'm listening,
So if.
times cosine B,
Cosine A, you got -3/5, right?
yeah,
Wouldn't for cosine B, wouldn't it just be 1/2? Cause if you.
that's the sine.
Oh.
Sine is 1/2. Sine is y, cos is x. So in the two different triangles, I'll call this x with a little bitty a. X for triangle A equals that. X for beta is square root 3. Does that make sense?
Alright.
How I've written that?
Cause it's on the X axis.
Y for alpha is 4. Y for beta is 1. That's a little b. Does that make sense? You good? I can do the same thing with radius, but I'll just leave it alone. Okay, so here's the formula. So now we just plug in. What do we already know? What is cosine A? Look right here. What's cosine A? -3/5. That needs to multiply times cosine B. Square root 3/2 minus sine A. Sine A was right up here. 4/5 times sine B, which was 1/2. Do I have a common denominator? Yes, you will. When you do this formula, you should have a common denominator every time. What is my common denominator on this particular problem? 10. I have -3 square roots of 3 minus 4. -3 square roots of 3, whoops, -3 square roots of 3 minus 4. That's the value there. I got so ugly. Let's try this again. -3 square roots of 3 minus 4.
Double up on the wording.
Sure.
What, yes?
When you're doing that, you want to put a little bit of the brackets there.
Double up?
Yeah,
What do you mean double up?
because you have to change the parameter of the thing.
Oh, they're already being multiplied. It was 5 times 2. So they were already 10. Okay, now let's do sine of A plus B. So sine of A plus B by formula. Does sine's formula change or the sign stay the same?
Change.
Stay the same. Sine stay the same, cosine changed. Cosine, they pair up, cos, sine, sine. Sine, they alternate. So it's gonna go sine A times cosine B plus cos A times the sine of B. So let's plug in our numbers and we'll call this wrap up this problem here. What was sine of A? I've already. It was 4/5. Good. Sine of A was 4/5. That needs to multiply times the cos of B, which is right here. Square root 3/2 plus cosine of A. I'll put that in parentheses, -3/5 times the sine of B. 1/2. Okay, let's simplify and we'll have this answer. Again, do we have a common denominator? Yes. Our denominator is 10. I have this time 4 square roots of 3 plus a negative makes it a minus. 3 times 1 is 3. And that would be the answer for part D. Which one? Here? A -3 times 1? All right. So let's walk through how we could do this with math getting really complex here.
Hey, man.
Here we go. Do you remember when we did inverses, how we restrict the domain? That's going to come in handy here as I draw this out. It says here, write the trigonometric expression sine of tangent inverse plus 1, excuse me, tangent inverse of 1 plus cosine inverse of x as an algebraic expression. So we're trying to find, and it says let u be this, v be that, and so we want to find sine of u plus v. So first off, what is a sine sum identity? If you are adding, does sine symbol change or does sine stay the same?
It's the same.
Hey Gabby, can you put up what you're working on? So it stays the same. So it's going to be sine u times cos v plus cos u times sine v. That's what I'm going to do mathematically. I'm going to substitute into that formula. There's the sum identity right there. We're going to substitute into that identity. First, though, we got to find out what those are. So come down here. This is u, and it represents tangent inverse of 1. Now, if it's a tangent inverse, that's telling you the y over x. So if tangent is 1, go to the back of your hand. If tangent is 1, it's an inverse, so we're looking at the back of our hand. Which finger do you have to bend to have a tangent value of 1? Okay, he said middle. Why did he say middle? I want you to think about it. Because if you bend your middle finger, how many y's do you have? Square root 2. How many x's do you have? Square root 2. What's the square root of 2 divided by square root of 2?
1.
1. So that value right here, what that means is we have the exact same x and y. Draw a line going up this way. You could put on there pi over 4. I didn't ask you to flip over your hand. Your middle finger is pi over 4. This would have the exact same x and y. So that y would be square root of 2. The x would be square root of 2. What is our radius or our triangle in this case? If we're bending and we're saying we have square root of 2, what would the radius need to be? 2. Very good. The radius is 2. So again, I'll do r with a u. The radius for u would be 2. This is x for u. This is y for u. That's that value right there. By the way, this would be a right angle, and that's where you'd place your theta. Okay, come over here. This says cosine inverse is x. Now, what is cosine as a ratio?
X and
I need to put that on there just to remind you. Okay. Here, cosine, what is cosine as a ratio? X over r. If this just says x, what does that mean our r is? Our r would have to be 1. Very good. Okay, so this time, since it's an x, I don't know where to put the angle. I don't know at all. So since we don't know where it goes, I'm just going to put it right in the middle. Here, I knew where to put it because the tangent is a slope that says it has a slope of 1. I knew it had a slope of 1. The slope was 1. I knew that had to be the case. Over here, I don't know where to put that angle. It could be anywhere. So I don't know where this goes. No clue. So for right now, I'm just going to put a question mark. Don't know where to put it. But I do know this. If I go down, they're calling the x value x. So just put that at x. And because it's x over 1, that 1 represents what value? The radius. Put r equals rv equals 1. My radius has to be 1. My x is just going to be x. Now, what's the missing value? We got to find y. Now, how can I find my y?
X is equal to 1, right?
No, x does not equal 1. The radius,
R.
r equals 1. R equals 1. So how do I find my y? I have to do the Pythagorean theorem. X squared plus y squared equals 1 squared. I'm doing the Pythagorean theorem. It says to solve this as an algebraic equation, that means solve it in terms of x. So I'm going to isolate my y to figure out what it is in terms of x. So how do I get y squared by itself?
You divide by y squared? Oh,
Nope.
subtract by y squared.
I'm going to subtract x squared first. So I have y squared equals, what is 1 squared?
Minus 8.
Okay, now how do you get rid of a square?
You square root.
Okay, now truthfully, when you add a square root that's not originally there, you need to remember that plus and minus could be potential answers, but not in this case because we're doing inverses. On inverse cosine, you cannot go down low. Remember, it was the first or second quadrant. So I have to be the positive here. Either way, first or second quadrant would have a positive y value. So this is the positive square root of 1 minus x squared. Okay, let's tie this all in to get our answer. To get my answer here this time of doing exactly what I did in the previous problem, but now with these crazy trig functions, I'm going to plug in. I need to know the sine of u. So go to triangle u. That's right here. Sine refers to, what's its ratio? Sine is, no, what's the sine ratio?
X over y over
Giovanni, what's the sine ratio? By letters. What letters is sines? Give me a guess. It's y over r. Our sine is y over r. In this triangle, what is our y value?
which triangle, the red one?
Yeah.
Square root is
And what's the r? 2. This needs to multiply times the cosine of triangle V. So come to this triangle down here. This is V. What is the cosine here? What's the ratio for cosine? X over r. So it's x over 1. Now that's going to add to cosine of u. So now I go back over here to u. What is the cosine of this triangle? Square root of 2 over 2. And that needs to multiply times the sine of triangle V. In triangle V over here, what is my sine? What's the ratio for sine? Y over r. So it'd be the square root of 1 minus x squared over 1. We'll simplify and we'll have our solution. We have the square root of 2 times x. What's our common denominator here?
2.
Our common denominator is going to be 2. We'll have a denominator 2. I'll have square root 2 times x. I'm going to put the x out front. Usually we do, if you have a number, you put it out front. So x square root of 2 plus, over here you can distribute, that's multiplying, 2 minus 2x squared inside the square root. That would be our solution to this problem. Now, that looks crazy, doesn't it?
Yes.
You ready to see something wild?
No.
Let's switch this here.
Sorry, I'm trying to let you. Can you see what you need, or you need me? I'm going to the calculator, and I want to prove to you what we just did works. Yep. Okay, so here's what I'm gonna do. I'm gonna prove to you this crazy thing. So they just gave us an x. Here, this is a cosine inverse. X has to be some number between -1 and 1. I'm gonna let y'all pick any number you want.
17.
No, it's gotta be between -1 and 1. Any number between -1 and 1.
0.17.
How about 0.17? I like that. And I'm gonna press enter. You see that's what the decimal is? Now what we're saying is the same. If I took the fraction of the denominator 2, x squared of 2. Now what do we just say x is? 0.17. If I did that times the square root of 2 minus, no, plus, sorry, plus square root of 2 minus 2 times 0.17 squared. I'm about to press enter. You know what the calculator is going to tell me the answer is? Same one as the other one. Let's see. Look at that crazy math. I'm going to do this again just to prove to you what we just did. In this case, what was x?
Let's just say x is like 1. Let's just say this.
X is 1. What if x was 1? If x was 1, we get this value. So I'm going to plug this in to our answer. But this time I'm going to say x is 1. So 1 goes there and 1 goes here. I'm going to press enter. Look what we get. Amazing. Did the math work?
Yep.
Someone say yes.
Yep.
The math worked. We simplified that crazy thing, believe it or not. That's what we just did there. I know it's wild. All right. How about DOL number 3?
What?
I'm not going to ask you to do all that, but what I am going to ask you to find is sine 2 theta and cosine 2 theta. You have formulas for these, or you could do a sine. You could do this as, if you wanted to. Sine of 2 theta is the same thing as sine of theta plus theta, and cosine 2 theta is the same thing as cosine of theta plus theta. I'll let you get started on that. All right. Example 7. It says find the solutions to the equations in the interval, verifying using a graphing utility. So here we go. We're going to finish this up. How do we find solutions? Well, you have to think through your identities. And I don't know how else to tell you to do this other than to think through what we're given here. What identity do you think we could use for sine of x plus pi over 3? Not a product property. This is a sum identity. It's a sign with a sum. This is a plus b. So here's what this right here is equal to, get ready, sine x cos b, cos pi over 3. That's sine a cos b plus cos x sine pi over 3.
Let me get, we're gonna do the same thing for the other one.
Oh, you're right on it. Now we're gonna do the same thing, but we have sine x cos pi over 3. But this time it's a minus. So minus cos x sine pi over 3. Does anything here cancel?
Everything.
No.
I mean, my bad. Cos x sine pi over 3.
Why are these two those cancel?
They have their opposite.
Opposite signs. So here's what I have. I have 2 of those. By this way, that needs to equal 1. Not the canceled part, but it originally equaled 1. So I have to include the equals 1. Okay, those 2 cancel out. So I have sine x cos pi over 3 plus sine x cos pi over 3. Well, that means I have 2 of them. I have 2 right here. I have 2 sine x cos pi over 3, not squared. That would be if they were multiplying. These are adding. Equals 1.
Is that our answer?
Not yet. Cosine pi over 3. We can reduce that. These are all multiplying. What is cosine pi over 3? Look at the pi side of your hand. Which one's that? The palm or the back? Palm. Bend your pi over 3 finger, which is index. When you're index, flip your hand over. What's the cosine there? 1/2. So we have 2 times sine x times 1/2 equals 1. What is 2 times 1/2? That cancels with that. That's 1. So we need sine x to equal 1. I'm going to get my answer from the unit circle. On the unit circle, sine is which variable? Sine is x or y? Y. We need to know, where is the y value equal to 1? Where is sine equal to 1?
Pi over 2.
Pi over 2. By the way, that's going to be our solution. I skipped an algebra step. If you wanted to write down all the steps, I should have said x is going to equal sine inverse of 1. And y'all are correct in saying that value is pi over 2. The reason I don't like writing sine inverse is technically that restricts half the graph. And you sometimes will have 2 solutions. If you just jump straight to the unit circle, you can get them from there. Pi over 2 would be our only answer. Now it says verify using a graphing calculator. How do I verify? You graph the 2 equations and you see where they intersect. So here's my first graph. sine of x plus pi over 3. Whoops. Plus sine x minus Asif. Come on now. Pi over 3. I want to know, where do those two functions intersect the line of 1? How many solutions do you see right there? Let me blow this up for you. Between 0 and 2 pi. That's the only area I need a solution. Well, let's see here. If I do analyze graph, 0, this solution, not 0, I'm sorry, menu, analyze graph. I'm not looking for the 0, I'm looking for the intersection. Where do these two graphs intersect? 1.57. What is that approximately?
1.6.
I mean, in terms of pies. If 3.14 is 1 whole pi,
Oh, that's like half.
that's half of a pi. So we got the correct answer here. That would be the correct answer. If you're like, wait, what? There's more answers. That's on another period. Over there, that's a different period. So that's the only answer we need. Okay, let's do this again. What about this one? If you look on your formulas, there's another formula. What's different this time when you look at it out? There's a 2. Go to your formulas. There is a double angle formula that has a what sine 2x is.
So sine 2 theta equals 2 sine theta cos theta.
Oh, I'm on the wrong side here. Double angle sine 2 theta is equal to 2 sine times cosine. So let's rewrite that out. A double angle sine 2 theta is equal to 2 sine x cos x. That's that part right there. The rest stays the same. Plus cosine x equals 0. That was a double angle identity. I just threw out right there. Double angle identity. Now I need to do an algebraic principle. To simplify this,
You can buy one.
that's what I was about to ask. Are these like terms? Can I combine them?
Yes.
Answer is no, because this has a 2 sine x with it. So what you do instead, if it looks at first like they should combine or simplify for that matter, but they don't actually because they're not like terms, you do a GCF. What did GCF stand for?
Greatest common factor.
You divide what's common. What do they both share?
My bad, I don't think.
They both have a cosine. So if I divide out a cosine from the front end,
Don't you have to do the same to the other side?
no, because GCF is the opposite distribution. Everything in math has its opposites.
Undistributed.
This is undistribution. There you go. What's cosine dividing out a cosine? 1. That was the greatest common factor.
And that's it.
Nope. Now, to solve this, what I'm going to do here is I have a zero product property. Remember that from algebra? Zero product property. That states if you're multiplying and you have a product of 0, there's only one way to do so.
Make it equal.
One of those factors have to be 0. Either cosine's equal to 0 or 2 sine x plus 1 equals 0. One or the other, if not both, have to be equal to 0. Zero product property there. Okay, so you could write these out into inverses, but I would do unit circle from here to solve for that. I'm going to do some unit circle here. Where would cosine equal 0?
No.
At these two spots. What are those spots? Pi over 2 and 3 pi over 2. If you want to do the inverse, you could write it out. X would equal cosine inverse of 0. But the two answers there are going to be pi over 2 and 3 pi over 2. Now I'm going to solve this one using a little algebra. What would I do first to the 1? So you'd subtract 1 and then you would divide by 2. I subtracted 1, I divide by 2. Again, now I'm looking for where is sine the y 1/2. You could do your inverse if you wanted to. Back of your hand, If you have sine on one finger, what are you bending? No,
The middle.
you're bending to have a one finger. What are you bending? The ring finger, which is a pi over 6. We're gonna have pi over 6 answers. One in the fourth quadrant
And wouldn't it be 7 pi over 6?
and one in the third quadrant. What pi over 6s are those? 7 and 11. So our total answers here? 7 pi over 6 and 11 pi over 6. This problem would have 4 different answers. This would be a set of answers. This would be a set of answers. All right, let's look at example C here. This time around, if I think through my identities, we don't have much that has a sine minus a cosine. So if I got my formula chart over here, I could show you. We don't have much that involves a sine minus a cosine. If you look up on here, you won't see. Here, again, this is a sine times a cosine, but we don't have much there, nor do we have on the earlier slide from our packet. The closest you can come up with Pythagorean. And so that's the idea I'm going to shoot for. That's a sine squared plus a cosine squared. So how can I start to get there? Well, algebraically, what I could do is, remember, whatever I do on the left, I have to do on the right. So if I don't want to make this too much more complex, I think the easiest way of trying to get to squares is to square both sides. When you square, you have to square the entire side. So this becomes a sine x minus a cosine x times another sine x minus cosine x, and that all should equal 1 squared, which is just 1. So I'm doing an algebraic principle here. Now I'll distribute. I'm going to have sine times sine right there. So that's going to give me a sine squared x, and then I'll have a sine times a negative cosine, and a negative cosine times a sine. So again, I'm going to have 2 of those. So minus 2 cosine sines. There were 2 of them, a sine times a negative cosine and a negative cosine times a sine. Since there's 2 of them, that's going to become negative 2 cosine sine. And then finally, we're going to have a negative cosine times a negative cosine, which becomes a positive cosine squared. Now, what can I do? Now I have my sine squared plus cosine squared. That's a Pythagorean identity. That sine squared plus cosine squared equals 1. And so what I'm going to say is that those two adding together is going to be 1. So I have 1 minus 2 cosine x sine x equals 1. And from there, I can do some algebra. I'll subtract by 1 on each side. So I have negative 2 cosine x sine x equals 0. Those both canceled. I can divide both sides by negative 2. And now that I know my solution will be from the zero product property, whenever sine x times cosine x equals 0. According to the zero product property, cosine x has to equal 0 or sine x has to equal 0. That's from the, where is it? Here we go. Zero product property is what makes that be so. Okay, so unit circle time. On the unit circle, where is cosine, or I could go ahead and write this as the inverse of 0, and x would equal sine inverse. But I don't like writing it this way because those two would restrict the graph. But here I'm just going to use unit circle. I want to know sine is the y. Where do the y values have zeros? That would be here and here. That would be the solutions for sine. The solutions for cosine would be when x is 0, which is these 2 locations. So going in order, we'd have a 0. I'd have a pi over 2. I'd have a pi. I'd have a 3 pi over 2. And obviously, you'd have a 2 pi if you went all the way around. Since I want my solutions between 0 and not including 2 pi, I'm going to just say it's 0, pi over 2, pi, and 3 pi over 2. Those are my solutions. on the interval from 0 to 2 pi. And I'm gonna go ahead and I'll add in the graph here to confirm my answers. Now, as I pick it up and I look, I have graphed my original, which was sine x minus cosine x equals 1. That's two different equations, and you can see there's two answers here, pi over 2 and pi. Now, you might be thinking, well, what happened to our other answers? Because we squared both sides. In algebra, when you square both sides, oftentimes you will create extra answers. So when I squared both sides, mathematically what happened is I created two extra answers. We created two extraneous answers. So over here, 0 was not a part of the solution set, and 3 pi of 2 over 2 was not part of the solution set. So those are what we call extraneous solutions, meaning mathematically they seem like they're solutions, but they're not actually solutions. Again, it happened because we squared both sides, and mathematically it worked out that way. But if you think about 0, if you plugged in the angle of 0, sine of 0 is 0, and then you would subtract cosine of 0. Cosine of 0 is positive 1. 0 minus 1 is negative 1, does not equal positive 1. But the squaring is what makes it math seem like it should work, because the squaring would cancel the negative. A negative 1 times a negative 1 would become positive. That's why that value doesn't work. Same thing would be with 3 pi over 2, same case. So those are extraneous solutions. So your true solution set would be pi over 2 and pi on the interval 0 to 2 pi. So that's the true solution set there. And we verified that from the graph. All right, let's look at example 7D. Now, as I look at this one, I see I have a double angle. So I'm going to start there. So according to our formula chart, if you went back in the packet, you would have the double angle for cosine as being cosine squared minus sine squared, or you could use 2 cosine squared theta minus theta 1, or you could use 1 minus 2 sine squared theta. Now that's the one I'm going to use. Why? Because I see I have a sine already. So I'm going to use the double angle identity shown right here. That's 1 minus 2 sine squared. So that's where I'm going to begin here, that this is going to be 1 minus 2, I already forgot. Is it 2 sine squared? Let's get that right. Yeah, 2 sine squared. And this problem is not using a theta, it's using an x. So I'll put that as an x plus 3 sine x minus 2 equals 0. That was using a double angle identity, is where I got that from. Okay, so now I'm going to simplify. I see I have some common terms here. I have a 1 and a minus 2. And so let's say negative 2 sine squared x plus 3 sine x. 1 minus 2 becomes a negative 1 equals 0. Now I have this as a trinomial. What I'm going to do, I don't like the negative on the front. Divide all these by negative 1. If I divide everything by negative 1, what that's going to do is make my equation 2 sine squared x minus 3 sine x plus 1 equals still 0. And now I'm going to do a trinomial here, a x method to solve this problem. This is A, that's B, this is C. If I do my factors of A times C, and that would be 2, and they need to add up to be negative 3. The factors of 2 that get to 3, ignoring the negatives for a moment, those values would be a 2 times 1. 2 times 1 is 2. 2 plus 1 is a 3. Now, to make it a negative 3, these both would need to be negative. Now, check it. When you multiply, they still give you positive 2, so we're good. So now what we do is we break apart the square. And so without simplifying, it would be 2 sine x, instead of 2 sine squared, the 2 sine x minus 2 times 2 sine x minus 1. All that equals 0. Now, right now, this is not truthfully simplified correctly, because this, if you multiply it out, would be 4 sine squared. Now, if you solve it, though, you'll still get the right answer. What should happen here is both of these get divided by 2. That takes care of writing this 2 twice. That would simplify out. So really, according to the zero product property, I'm going to be solving that sine x minus 1 equals 0, and 2 sine x minus 1 equals 0. I'm going to do that by the zero product property. Okay, so here, I'm looking for where sine x equals +1. When I add the 1, where does sine x equal 1? Here, I'm going to look for where does sine x equal +1/2. And so if I added in a unit circle here, remember sine is the y's. I need to know when y is 1, which is going to be this spot at pi/2. I also need to know when sine is 1/2, which would be over here and over there. Sine of 1/2, if you did this as an inverse, if you looked at the back of your hand, where would sine inverse be 1/2 back of your hand? You'd bend one finger, which is your ring finger. Flip over your hand, you'd see that's pi/6. And so that's where this pi/6 comes from for this answer. And the second quadrant would be a 5pi/6. So those would be our three solutions here. I'll go ahead and put this one on sine inverse of 1. And that would be the pi/2. That's where that answer comes from. So right now, it looks like our answers should be going in order: pi/6, followed by pi/2, and then 5pi/6 on the domain of 0 to 2 pi. Now that's what I think this is going to be. Let's check our graph and make sure. So we have y equals, we're going to do the cosine of 2x plus 3 sine x minus 2, and I want to compare that to 0. I'm looking on this domain. I'm going to zoom in just slightly here. It looks like I have pi/6 as a solution, pi/2 is a solution, and 5pi/6 is a solution, just like we thought. All right, now let's look at part E here. So let's look at this formula. What stands out to me is we have sine x times cosine x, and this is an identity. We have something similar to sine x times cosine x, and it's right here. It's the double angle. Sine 2 theta equals 2 times sine theta cosine theta. So that's the identity I'm going to use here. But I just have to get this in the right form. So what I'm going to do is I'm going to multiply both sides by 2. And if I do that, I now have 2 sine x cosine x equals
1.
1. Very good.
Wait, the sine and the cosine are together. So
There, yep, they're
so
together.
yeah.
They're multiplying together. Okay, so according to the formula chart, 2 cosine times cosine is equal to, let's go back to that identity. Sine 2 theta is equal to 2 sine cosine. So that's what that's going to be equal to. That right there equals
Sine 2 theta.
sine, in this case, instead of 2 theta, I'm going to say sine 2x. That is the double angle identity.
That's it.
Close to being it. Now, once you have the trig function isolated, I think at that stage is when I would recommend for you to use a unit circle to solve for your solutions. We want sine to be 1. Sine is which letter?
Y.
Okay, so technically what I should do is write that 2x,
Wait, we wouldn't divide that into it.
you can't divide the 2 because that's inside the sine. But what I can do, that's inside the sine function, what I can do is its inverse.
Into 2x.
And that's what I'm going to do here. Where does sine equal 1? At half a pi. Sine is 1 at this location there, which is half of a pi. So here's what that means. I'm going to substitute that in. That is half of a pi. That is what that equals. And that's the only place sine is 1. So 2x equals half of a pi. And so if 2x equals half of a pi, what would 1x equal?
A quarter.
That's right. Pi divided by 2 divided by another 2 is the same thing as pi divided by 4. Now, this normally, we'd say this is true on any solution starting at 0 all the way around until 2 pi. So that's true from 0 to 2 pi. That should be our only solution. Now, what I'm going to do is confirm it. So I'm going to go to my calculator. Here it is. I'm going to graph. This is important that you know how to do this. I'm going to graph the left side of the equation. sine x times cosine x, and on Desmos put parentheses after sine and cosine. It needs to be equal to 1/2. And what I've added here are the two boundaries. We're looking between 0 and 2 pi. So this just tells your eyes where to look. How many solutions do you see there?
2.
2, which is strange that we have 2, and I'll show you why. Why is that not showing up right? I'll show you what this is, pi over 4. I'll get there in a second, and what this answer is. But it's strange it's not giving me the pi's right now. But I'm about to show you that that is pi over 4. Let me just do it right now. Pi divided by 4. Compare your decimals. This is 0.785. What is this decimal?
75.
That's the answer there. Okay, so now, why is it that there's a second answer? Here's why. And this is why, unlike the previous problems, I wrote 0 and 2 pi. When I actually solved this, we got down to here and we said 2x equals the sine inverse, which is pi over 2. Well, that dividing by 2 doesn't just change this answer. Technically, I should have divided,
By 4.
nope, all of them should have been divided by 2, which means this boundary should have been divided by 2, and this boundary should have been, which means my answer, because it was 2x here, that's why. And so you know how I just divided this part of the answer? And so that's why I wrote that in there, because I knew it was going to come back. And so this is actually not true on 0 to 2 pi, but it's true on 0 to 1 pi. Now, what would be the answer if it was true on 0 to 2 pi? Well, we've now decided that the period is not 2 pi, but the period is 1 pi. So our other solution would be 5 pi over 4. It's going to be 5 pi over 4 because you just add a pi. Now on 0 to 2 pi. Yep. And so now let's go confirm this. I'm going to go ahead and box it because I already know the answers. We just looked at them. Let's go confirm this on the graph. We confirmed that that is 1 pi over 4. Let's see if that's 5 pi over 4. 5 pi divided by 4. Is it giving us the same two values? Oh, I see why. I was clicked on the blue line. There we go. That's the easier way of doing it. What pi's are they giving us? Pi over 4 and 5 pi over 4. All right, last one for me. Example F. Now, this one can look tricky. It's actually very simple. Here, what's the big things going on with the trig? I have a sine minus a cosine. This has a coefficient with it. So earlier on the problem, I said there's not much that's in terms of a sine and a cosine unless it's one of these type formulas, but the last one didn't fit the bill. This one does. We have a coefficient. How many sines would you say there are right now? 1. So I have two different coefficients here. If you have two different coefficients, this is either a sine or a cosine formula because, well, we don't know what it is yet, but let's just go over here and look at them. This is either, or it has to be a sum, a sine difference. Why does it have to be a sine difference? Because cosines, look at cosines formulas. What comes in the front end? What's positive? The cosine pair. This has a negative cosine, so it can't be a cosine formula. And then sine symbol stays the same. So this is a sine formula where they're adding up. To make it's going to be, yes, sine A plus B. So this formula right here, this is a sine sum identity. This is the same thing as sine of my two angles. I said sum identity. It's not the sum, it's the difference. X minus, now do we know what the other angle is yet? No. So you know what, maybe I should write it this way. That formula is the same thing as sine, I'm going to call, we have some unknown value. Let me write it over here. We have a y of 1, an x of square root of 3. I want you to think through this on the unit circle. Whoa. Let's see if you can get there. I'm I'm thinking through a better way of doing this. I know what this value is going to be. So before I write it this way, I want to do like this. How about this? If I divide everything by 2, I'm about to show you why I'm doing this. We would have 1/2 times sine x minus square root of 3 over 2 cosine x equals 1/2. Now, why would I do it this way? Because I can use my hand trick to figure out what is this. This has to be, if it's a sine formula, this is the cosine, this is the sine, because sine's formula, let me go back to it. Sine's difference formula, it's a sine A times cos B minus cos A sine B. I could reorder it if you wanted to make more sense out of it. So this is sine, that's the A. This is the cosine of B minus, this is the cosine of A. This is the, no, sorry. This is the cosine of A. We don't know what A is. Times the sine of B. Now, what is my angle? What would have a cosine of 1/2? I'm going to use a different variable. Cosine of 1/2 and a sine. That's right. Of square root 3 over 2. You could do a hand trick, but you'd find out it only happens at one place. Whereas cosine 1/2 and sine B is square root of 3 over 2, it's going to be here at pi over 3. That's this angle there. That's where that comes from. So this is a long way of getting to. This is sine x.
The other one, yeah.
Yes. That should be 1/2. Sine x times cosine of pi over 3. I'm replacing 1/2 with cosine pi over 3 minus cos x sine pi over 3 equaling 1/2. Why did I do all that? Because now I can finally say this is a sign difference identity. This is the difference identity. So it took a lot of setup there. I can simplify that whole equation to be sine of, what are my two angles in here? X and subtracting pi over 3. And that should equal 1/2. Okay. Technically, I should write inverse on the side if I wanted to keep going. But you could just go straight to a unit circle, which is what I'd recommend you do. So let's go to a unit circle. And sine is which variable? X or Y? I want to know when the y's are 1/2. That means there's two of them when y is 1/2. There's a y this way when we're 1/2 and a y this way. Not pi over 4. You're thinking about the back of your hand. You need to bend one finger. Which finger? Pi over 6. That would be pi over 6. What pi would this be over here? This one right here is pi over 6. This would be 5 pi over 6. Now remember, the calculator would not show you this one because inverse is restricted, but truthfully, the original was not restricted, so I should have both. I have those two answers. But that's when x is, if it were just x, but this is x minus pi over 3. So to take care of my answers, this time we'll do it before we go to the calculator. You would say x minus pi over 3 equals that pi over 6. And the other solution will be x, minus pi over 3 equals 5 pi over 6. Algebraically, how would you solve both of these situations? You isolate the x. Add pi over 3. When I add pi over 3, that goes away. When I add pi over 3, that goes away. And so pi over 6 plus pi over 3, that's the same thing as 2 pi over 6. It is half of pi. Pi over 3 plus pi over 6 is half of pi because this is 2 pi over 6. 1 pi over 6 plus 2 pi over 6 is, that's right. Let me just go ahead and write that out. Pi over 6 plus 2 pi over 6. Down here we have 5 pi over 6 plus 2 pi over 6. Which gives us our two answers. 1 pi over 6 plus 2 pi over 6 is 3 pi over 6 or half a pi. And then here, 7 pi over 6. Those are our two solutions. Pi over 2, comma, 7 pi over 6 on 0 to 2 pi. Okay, now you could say, well, didn't we subtract? Yes, but that's not actually going to change anything. That'll still be the solutions this time around. And I'll prove it to you now. Now that we have all of that, I'll go to the graph and we'll see our two answers here. So we this time started with sine x minus a square root of 3 cosine x, and that needed to equal 1. How many solutions do you see? 2. Let me highlight this graph. Pi over 2 and 7 pi over 6. Is that what we had? You bet. So now we'll go on to your DOL. You can finish up with this one. You can verify using a graphing utility that might help you out. But I'll give you a hint. If I were you, you could do a Pythagorean identity if you look closely, and there might help yourself out to start. There's a lot of different ways you can go about this one. But if you do the Pythagorean, you could cancel out some terms that are alike. Anyways, I'll let you get started.